Okay, here's another example. Let's consider again the rotating rectangular loop, this diagram here. This time we compute the electromotive force from the equation minus d phi by dt. The flux through the loop equals its area, A, multiplied by the component of B perpendicular to the area, that is B cosine theta. You can see that that part there is B cosine this angle between them. This is also equal to the magnitude of B multiplied by the projected area shaded on a plane, the xy plane perpendicular to B. So we can write the magnetic field flux equals B dot dA. So we can just write down BA cosine theta. If we're looking at time, we can rewrite theta as the angular frequency times the time. Then the electromotive force then obviously is the minus of this. So we can see that if we differentiate this term here, we get, now that we normally get the minus, because the minus is in front, we've got a plus here. So when we differentiate that, we get WBA sine WT. So the electromotive force due to this changing flux here, the spinning round, is in agreement to how we calculated it before. So note that the maximum value of E when theta equals 90 and the flux through the loop is 0, and that electromotive force equals 0 when the angle equals 0 and flux is at the maximum. The EMF depends not on the flux through the loop but on its rate of change. So that's an example of how we got to this before, but this time we've just used this equation here, where we got this before previously. Now we're using this and we've got the same thing by just looking at the change in flux and not the motion of the B cross V.